Hi, myself Shubhankar, and I work at RS Software. And today we are going to discuss about a fraud and risk management system that has been built by RS Software and how we have used YugabyteDB there. So this is me, Shubhankar, and I work at RS Software as data architect. And it's been over 8 years now I'm with RS Software, and my primary focus is in designing and optimizing data architectures for you know our payment related systems, including this fraud and risk management. So RS Software is actually a global pioneer in digital payments, and for moreover 30 years till now. And you may know RS Software as the original architect of UPI, that's Unified Payment Interface, BBPS, Bharat Bill Payment System, and also our National Enterprise Fraud and Risk Management System. That's what we are going to talk about today. And we are a product and platform-led organization. We have our products deployed across geographies, catering to all real-time payments, card payments, fraud and risk management system, connectors, overlays, etc. In 2024, total 49% of the global digital payment volumes is actually processed on platforms that has been built by RS Software. And recently, you may have heard that UPI has already surpassed Visa in terms of number of payments processed. So our current approach or our current solution that was we have created previously is to serve 2000 TPS. And payments in India have grown rapidly. So we did some scaling with the infrastructure which we have, and it did support till 6000 TPS. And as we have seen, the digital payments is growing rapidly fast. There was a requirement to scale up the infrastructure and go for a better solution. And the issues which we have with our current TV infrastructure was that real-time data ingestion was not happening. So we had to batch and we had to run another application to go for a real-time data ingestion. And also query performance degraded day by day. Since our data volume grew so much, we have seen an increase in query latencies. And it didn't have any support to non-key queries. It didn't have a proper indexing approach for non-key queries, our current DB infrastructure. About that, the operational overhead for our current DB infrastructure was much more. Like we had adding nodes, dropping nodes, all of them were costly. And it didn't have actually any asset guarantees. And also what we have few Postgres related queries which we had to run so that it can generate few analytical and reporting tools or few analytical and reporting queries. So we had to take another application on top of that so that we could run all these queries. So which led us to to an improvement at DB stack. So the improvement scope was to have a DB which will support a ingestion rate over 100,000 per second, and with a stable performance you could say that 40,000 to 80,000 records per second. And our data retention policy was to have data in our DB system for 180 days at least. Beyond that, we had to purge. And latencies we have to have as low as below 30 milliseconds. That's how our read query is gonna be under 30 milliseconds. And we have to have relational capabilities since we have PostgreSQL related queries which we have to run in our database. So it has to be a Postgres compatible, and also non-key query search has to be efficient enough. which will help us, running those post reporting and analytical queries. So it would be better if it could support secondary indexes as well. And lastly, it has to be an open source solution. So it has to be cost effective. It has to be an open source solution. So for this, what we did is that we have chosen two databases, YugabyteDB and CockroachDB. And we have done separate benchmarking on both of the databases. On Yugabyte and Cockroach, primary key related queries are really fast. We have seen that. And with an introduction of additional secondary indexes, we have seen ingestion rate dropped really fast. Comparing this ingestion rate drop, we have seen YugabyteDB performed better than CockroachDB here. And also in Cockroach, we had to use a separate load balancer to balance the load between the nodes. In YugabyteDB, it did through its inbuilt YSQL driver. So here we are thinking about using YugabyteDB YSQL flavor. So we did those benchmarking. We have seen the performance drop in both of the databases. So we have chosen YugabyteDB because it performed better than CockroachDB while adding more indexes to the tables, and also all the relational capabilities and also PostgreSQL features it has compared to CockroachDB. So this is what the current architecture of our application is. This is how YugabyteDB is deployed in our fraud and risk management system. So what happens is that we have two separate YugabyteDB instances. Here, what we did is that initially we thought about going for YugabyteDB's active-active database approach, but with the data volume we have and the kind of DPS we are thinking about reaching, we thought it would be a better solution to have database level application from the application level itself. So that's why what we did that we installed two separate YugabyteDB instances in both of our DCs. Both of them actually are active-active. Both of them accept writes and reads. But the writes here, it has been pushed through a Kafka consumer, which actually writes to both of these YugabyteDB instances simultaneously. And also read happens here simultaneously through both of this, from both of this YugabyteDB cluster. So each cluster actually has 30 plus nodes. Currently it has 30 nodes, and each node has 64 vCPU. So 30 data nodes, each data node has 64 vCPU, and we have 3 name nodes in every YugabyteDB name nodes or master nodes in every YugabyteDB cluster. And here what we have gone with 9 nodes, and we kept on gradually increasing the nodes as our ingestion throughput. We had to match our ingestion throughput rate, so we kept on adding new nodes every other day, and we have seen the improvement in ingestion as well as in query read. Query reads also not much affected. It was really fast. So it did meet our SLA, and also the ingestion throughput where we are able to meet with 30 nodes per site. So ingestion throughput requirement was to have 40,000 to 80,000 records per second each site. So that's how we have implemented. We have two separate YugabyteDB instances across two separate DCs. Both of these instances are active-active. They accept reads and writes simultaneously. Each site actually has 30 data nodes and 3 name nodes or master nodes. And real-time data ingestion happens through a Kafka consumer, which writes to both of these YugabyteDB instances simultaneously. Also, reads and updates are passed through a user-defined function here in YugabyteDB. Why did we use user-defined function? Because we have different type of payment channels. We have like UPI, IMPS, and all. We have different those payment channels. So for each of these payment channels, we have different type of message types. Message types are different. So we had to create a few user-defined functions for those each channels. For that, we take input a kind of message type, and it will basically insert or update the record in the database. And here what we have that for a particular channel, let's say our data requirement is to have 600 to 800 millions of records of insertion actually for a single day. So what we initially did is that we gone for a single table for that type of insertion. So it would, a single table will hold 180 days of record, and each days of record has 600 to 800 million records. But what we have seen is that since our record, with this number of records, our ingestion rate were not stable, and also adding secondary indexes, running and reporting and analytical queries on previous days of records actually affected the ingestion. Also, we had to maintain a data retention of 180 days. So for that, what we have done, we have gone for a range partition. It's a everyday range partition. Like that particular table is partitioned day wise. So every single day's partition holds around 600 to 800 million records currently, and it could reach up to 1 billion records every single day for a particular channel. And for other channels, what we have done, we have gone for a monthly partition. So data retention there were moved to 210 days. And with this approach, what we have seen, we were able to meet our real-time SLAs under 30 milliseconds, also maintaining the ingestion speed at peak 40 to 80,000. So this is how our application is impacted with introduction of YugabyteDB in our application. So YugabyteDB's PostgreSQL compatibility helped us to run those Postgres supported analytical and reported SQL queries efficiently. We didn't have to change much. We just did some tuning because according to YugabyteDB's distributed approach, and that helped us running those queries quite efficiently. And also its ACID compliance and strong consistency is helpful. We have introduced secondary indexes on non-key queries so that we could, run those reporting and analytical queries efficiently in YugabyteDB cluster. And the cluster management is quite helpful. Using the UI, we could simply add or remove nodes quite easily. Adding or remove nodes previously were troublesome. We have to wait till the entire data gets copied to the new node, then it will accept writes and all. But with this approach in Yugabyte, what we have seen that I just had to add a particular node in the cluster, and once few tablets get copied, it accepts writes immediately. So, and in the background, it just copies data, continuously copies data. So it acts as an active node once few tablets get copied to that particular newly added node. So we didn't have to do much anything there. So this was actually quite helpful. And with this YugabyteDB architecture, we were able to uh, maintain the ingestion rate at 40,000 to 80,000 per table, and records per second, and also it has moved till 100,000 records per second as well. And latency were reduced as below as 30 milliseconds with this architectural approach. So this is what we have achieved with Yugabyte in our current application. Currently, it handles or it ingests 600 to 800 million rows every single day for a single channel. And average peak TPS actually reached to 40,000 to 80,000 records per second. And read queries were with primary keys were as slow as it was within the SLAs between uh, 0 to 30 milliseconds. And in this current infrastructure, we were able to ingest data 1 billion per day. So if this infrastructure could handle 1 billion records per day, if we have also optimized it for to handle more than that, because we will continuously continue adding nodes to the cluster so that it could handle more records. And we have also seen that it happens actually with this YugabyteDB. So while going for the solution, we have seen that a particular table with a particular secondary index, it was able to handle with that many number of nodes. It was able to handle 180K write operation per second. And what we have seen that once we kept introducing secondary indexes. So let's say a particular table has 10 to 12 secondary indexes, and that table is, daily partition. So every partition has 10 to 12 secondary indexes. So we once we keep going on adding secondary indexes, we have seen a throughput, reduced speed in throughput. So from 180K, it reduced, but which was kind of expected, I think, because indexes were treated as separate tables here, so it's kind of expected. So what we did to maintain the average peak TPS of 40 to 80,000, what we did, we have gone for a single index for the first day itself, and non-key queries searches were redirected to another active alternate data source to avoid any delays, and secondary or backfill indexes were added after the first day is completed. So with this approach, we were able to achieve that peak TPS of 40,000 to 80,000 with 30 nodes. And also initially what we had done is that we had used manually pre-splitting of tables to control the number of tablets and balance distribution. But once data volume grew, and also with that number of peak TPS, what we have seen, it required more and more tuning, manual tuning actually. So what we did is that we had switched to automatic tablet splitting, which actually reduced our operational overhead and also improved data distribution across all the nodes. So thank you. That's how we have used YugabyteDB in our current architecture.